You know how a broken arm gives you a clean, really satisfying x-ray? Like there's a jagged white line on a black background, and the doctor just points a pen at it and says, there is your problem.
Right, it's completely binary, broken or not broken.
Yeah, exactly. We crave that kind of visible physical categorization when we try to understand the human body. But the moment you step into the world of cognition, that x-ray machine just shatters.
Oh, absolutely.
Because we're trying to find the physical, biological location of like a mind changing. Where is a gut feeling located? What is the exact cellular moment of visual input transforms into a subjective preference or, a conscious thought?
It is the absolute definition of diagnostic muddy waters. I mean, trying to isolate consciousness in a scanner is like, well, it's like trying to find the concept of justice by just looking at the ink on a legal document.
Wow, yeah. That's a great way to put it.
The physical medium is there, obviously, but the phenomenon is an emergent property of millions of moving parts. So we are transitioning from the absolute basics of sensory perception, which we mapped out previously, into the foundational building blocks of higher thought.
Right.
And this is where the biology gets infinitely more complex, but also incredibly elegant.
Which is the entire mission of our deep dive today. We are picking up the second half of our journey into how the brain scales up. We've already looked at how simple, noisy sensory decisions are made.
Right, like deciding which way a flock of birds is flying.
Exactly. But today, we are figuring out how those same primitive circuits scale up into complex probabilistic reasoning, into the subjective value judgments that make you, and ultimately into the mystery of conscious awareness itself.
It's a big leap.
It's huge. So whether you are a neuroscience student, a clinician, or just insanely curious about how your own mind generates a conscious thought to understand the words I am saying at this exact moment, this deep dive will give you the exact framework to understand your own awareness.
We should probably ground ourselves in the core mechanism we established previously because, well, it is the engine for everything we will discuss today.
Yeah, let's do a quick recap.
Okay, so the brain acts as an accumulator. It gathers noisy, imperfect samples of sensory evidence from the outside world, and neurons hold on to that evidence, just kind of adding it up over time.
Well, accumulating it.
Exactly. And when that accumulated evidence crosses the specific threshold, a decision is made. So a monkey looks at dots moving on a screen, visual neurons feed that data to the parietal cortex, the firing rate climbs, and boom, an eye movement is triggered.
Which makes total sense for raw physical data, like light hitting the retina. But moving from dots on a screen to real-world reasoning feels like an impossible leap to me. Because how does my brain handle evidence that isn't just physical light or sound waves? If I am trying to weigh abstract concepts like reading the room during a tense meeting or making a financial decision, I'm not just accumulating photons, I'm reasoning.
Right, and to bridge that gap, we have to look at perceptual decision-making as a mathematical model for probabilistic reasoning.
Okay.
The brain doesn't just process what is happening right now. It processes the probability of what might happen next, based on abstract clues. A classic scenario from the text to illustrate this is deciding whether to carry an umbrella when you leave your house.
A decision I routinely mess up, honestly. I mean, I either end up completely soaked or I carry an umbrella around all day in the blazing sun looking like a fool.
Well, we all do, because the variables are constantly shifting. Imagine you are heading out for the afternoon, and you have to synthesize 4 distinct, entirely abstract clues to make your umbrella decision.
Okay, lay them on me.
Clue number 1, yesterday evening you heard a weather forecast predicting a chance of rain. Clue number 2, you look out your window this morning, and the sky is mostly clear, maybe a few wispy clouds. Clue number 3, you glance at a digital barometer on your wall, and it shows a slight drop in pressure over the last hour. And clue number 4, you look down at the street, and out of 12 pedestrians walking by, exactly 1 is carrying a folded umbrella.
Man, every single one of those is a completely different data format.
Exactly.
You've got a memory of spoken language from a meteorologist, a direct visual assessment of the current sky, a mechanical numerical reading from a device, and like a behavioral observation of strangers.
And none of these indicators offer a 100% guarantee. They are probabilistic cues. To make the most rational decision, the brain must consider each piece of evidence and evaluate its conditional probability.
Conditional probability, meaning what exactly?
It asks how likely is this specific observation if it does rain later versus how likely is this observation if it does not rain. You're constantly relying on learned estimates of these probabilities from your past experiences.
So my brain is basically querying my memory banks. It's asking, historically speaking, when I see a clear sky at 8 a.m., how often does it actually pour at 3 p.m.?
Formally, this calculation relies on something called the likelihood ratio. Let's isolate just the weather forecast. Suppose years of living in your city have taught you that when the local news says chance of rain, it actually rains about 1 out of every 4 times.
Okay, so a 25% chance.
Right. That means the conditional probability of rain given that specific phrasing is 1 in 4. The probability of no rain is 3 in 4. The likelihood ratio is the ratio of those two probabilities, so 1/4 divided by 3/4, which simplifies to 1 to 3.
A 1 to 3 ratio, or about 0.33, which is significantly less than 1.
Yes.
So even though the weather person used the word rain, the mathematical reality of my life experience means that forecast actually leans heavily toward no rain.
Exactly. Any likelihood ratio greater than 1 favors the event happening. Anything less than 1 favors it not happening. So you have a distinct likelihood ratio for the sky, the barometer, and the pedestrians.
Okay, I follow you so far.
Now, standard probability theory dictates that to find the total combined probability of rain, you must multiply all 4 of these individual likelihood ratios together. If the final multiplied product is greater than 1, you take the umbrella.
Okay, wait, I have to push back here. Humans are notoriously aggressively terrible at math.
Very true.
I mean, if you ask me to multiply 0.3 by 1.5 by 0.8 in my head while I am tying my shoes and trying to find my keys, I am going to fail completely.
Of course you are.
So you were telling me an animal that can barely calculate a 15% tip at a restaurant is subconsciously multiplying complex fractions on the fly. How is that physically possible for a biological cell?
It isn't. And your skepticism is entirely justified. Multiplying fractions is computationally expensive and biologically messy. This is where the evolutionary elegance of the brain really shines.
Okay, so what does it do?
The brain does not multiply these ratios. It simply adds them. But to do this without breaking the laws of probability, it uses a brilliant mathematical trick. It takes the logarithm of the likelihood ratio.
Logarithms. Okay, we are diving deep into high school algebra now. Remind me how taking a logarithm solves the multiplication problem.
A fundamental property of logarithms is that the logarithm of x times y is mathematically identical to the logarithm of x plus the logarithm of y.
Oh.
So by converting the raw probabilities into log likelihood ratios, or log LRs, multiplication is transformed into simple addition. The brain takes complex probabilistic reasoning and just flattens it into an additive scale.
So instead of trying to multiply 0.33 by 1.5, the brain just converts those to their log values and stacks them like weights on a balance scale.
Think of it exactly like a balance scale. A positive log LR is a weight added to the rain side. A negative log LR is a weight added to the no rain side. Let's look at that fourth clue you observed, seeing exactly 1 person out of 12 carrying an umbrella.
Okay.
Suppose your experience tells you that seeing one cautious person with an umbrella is equally likely on a day it rains as on a day it doesn't rain. The probabilities are 50-50.
So the likelihood ratio is 1.
And the logarithm of 1 is 0.
Oh, that's brilliant. So a totally uninformative observation literally has a mathematical weight of 0. It adds absolutely nothing to the scale. It doesn't push my decision toward rain or toward no rain. It just washes out of the calculation entirely.
This additive mechanism is so crucial that neuroscientists actually wanted to prove it wasn't just a theoretical model, but a physical reality happening inside individual cells.
How do you even prove that?
They designed an incredibly sophisticated experiment with monkeys, which serves as a landmark in understanding reasoning. They wanted to see if neurons could act as biological abacuses, performing this logarithmic addition in real time.
But how do you train a monkey to understand the probability of rain? Or like anything abstract like that?
You strip away the weather and use pure, abstract visual symbols tied to a reward. The monkey sits in a specialized room facing a monitor. It is trained to make a simple choice, look at a red target on the left or a green target on the right to get a drop of juice.
Okay, pretty standard setup.
Right, but to know which target hides the juice on any given trial, the monkey has to interpret a sequence of 4 abstract shapes that flash on the center of the screen, one after another every half second.
So this is mirroring the umbrella problem perfectly. 4 sequential abstract clues.
Exactly. The researchers created a vocabulary of 10 possible shapes: a triangle, a square, a star, a Pac-Man shape, and so on. During months of rigorous training, the monkey learns that each specific shape has a different predictive reliability.
Meaning what?
For instance, the star might be a massive predictor that the juice is at the red target. The square might be a weak predictor for the green target. The researchers mathematically assigned a specific rigid log LR to each of the 10 shapes.
The monkey is watching this sequence unfold. Star. Half a second later, square. Half a second later, triangle. It has to combine these weights to make a final bet on red or green.
And as the monkey does this, the researchers are recording the electrical activity of single individual neurons in the lateral intraparietal area, the LIP. This is located in the parietal cortex, which sits near the top and back of the brain. It's an area heavily involved in spatial attention and eye movements.
Wait, isn't that the same area that accumulates the physical motion of dots that we discussed before?
The very same. But now it's not looking at physical motion, it's looking at abstract symbols. Imagine we are monitoring one specific LIP neuron that is biologically wired to trigger an eye movement to the green target.
Okay, so this cell's entire job, its reason for existing, is to shout, "Go green."
Exactly. Let's watch the firing rate of this single cell as the sequence plays out. The first shape flashes on the screen. It's a shape that weakly predicts green. Instantly, the baseline firing rate of the neuron steps up just a little bit. The electrical spikes become slightly more frequent. The cell is holding that new, elevated rate.
It added a small weight to the green side of the scale.
Then, half a second later, the second shape appears. This shape is a strong predictor for the red target. This is evidence against green.
So what happens?
The firing rate of our go green neuron plummets discretely. It drops below its original baseline.
It's actively subtracting on the weight.
And then the third shape appears. It's a massive predictor for green. The firing rate rockets upward, creating a huge spike in electrical activity, holding steady at this new high plateau.
Wow.
The vertical position of this firing rate, the literal number of electrical spikes per second precisely, mathematically tracks the cumulative sum of the log likelihood ratios of the shapes the monkey has seen so far.
Okay, let's unpack this because that is staggering. A single cell is doing Bayesian statistics. But how does it do this? Because we already agreed the cell doesn't know math. How does the biological hardware know that a star means add a lot of spikes and a square means subtract a few spikes?
It comes down to the brutal, beautiful efficiency of synaptic plasticity. During those months of training, the visual cortex is learning to recognize the shapes. The neurons in the visual cortex that fire when they see a star send physical axonal connections to our LIP neuron.
Right.
Because the star frequently leads to a reward at the green target, the synapses connecting the star visual neurons to the go green LIP neuron are physically strengthened. They become thicker, more sensitive.
So when the star appears, it dumps a massive amount of neurotransmitter into the LIP neuron, causing a huge spike in firing.
Conversely, the visual neurons that recognize a red predicting shape develop inhibitory connections to our go green neuron. When that shape appears, it releases inhibitory neurotransmitters, suppressing the LIP neuron's firing rate. The math is solved by the physical architecture of the synapses.
The synapse is the logarithm. The thickness of the connection is the mathematical weight.
Exactly. The brain has taken the simple, primitive mechanism of adding up sensory evidence to a threshold, the same mechanism a fish uses to decide to swim left or right, and co-opted it for abstract, learned probabilities. It proves that perceptual decision-making is the foundational architecture for complex, rational thought.
This makes perfect sense for things with objective outcomes. I mean, a meteorologist predicts rain, and eventually the sky either opens up or it doesn't. The monkey predicts the juice is at the green target, and the juice is either there or it isn't.
Right. There's a correct answer.
The universe provides an objective answer key to calibrate those synaptic weights. But human life is rarely about objective answers. What happens to this biological abacus when there is no correct outcome? Let's say I'm looking at a menu and choosing between a cup of coffee and a cup of tea. There is no objective reality where coffee is universally correct.
That transitions us into a wildly complex domain. Decisions about preference, which require evidence about value. You are no longer accumulating evidence about the physical state of the world. You are accumulating evidence about your own internal, subjective appraisal of the world.
Which feels inherently unscientific. I mean, how do you measure the physics of a preference?
You start by categorizing where values come from. Some values are deeply innate, hardwired by millions of years of evolution. The preference for sweet tastes and the aversion to bitter tastes are virtually universal across the animal kingdom.
Sure.
Sweet signals dense caloric energy, which promotes survival. Bitter signals alkaloids, which are often poisonous.
So my brain doesn't need to learn that sugar is good. It comes pre-installed with that bias.
But the vast majority of the values that govern human behavior are entirely learned. You are not born valuing the bitter, complex taste of black coffee, or the acoustic arrangement of a specific jazz song, or the aesthetic lines of a particular sports car.
Right, those are acquired tastes.
These are constructed values. To understand how the brain decides between coffee and tea, we have to look at how it physically stores those constructed values.
Okay, let's map the anatomy. Where does the value of a cup of coffee actually live in my brain?
It's segregated into two distinct neural populations based on what aspect of the value you are processing. First, deep in the subcortical regions of the brain, you have the striatum. The striatum is intimately connected with the motor cortex. Neurons here tend to encode the value associated with a specific action.
Meaning the physical effort required, like the value of reaching my arm out, grabbing the mug, lifting it to my mouth.
Yes. If the coffee mug is placed unusually far away, requiring you to stretch awkwardly, the striatum evaluates the cost of that action against the benefit.
Okay, what's the second population?
The second population is located much higher up, primarily in the orbitofrontal cortex, which sits just behind your eyes, and the cingulate cortex. Because the orbitofrontal cortex receives massive inputs from all your sensory systems, taste, smell, vision. The neurons here encode the value associated with specific items, independent of the motor action needed to acquire them.
So the orbitofrontal cortex evaluates the coffee itself, the aroma, the warmth, the caffeine. It is putting a subjective price tag on the item, while the striatum evaluates the cost of the physical work.
Exactly.
So how do these two systems actually generate a choice when the waiter asks what I want?
The underlying strategy is remarkably identical to the perceptual decisions we just discussed. In the motion task, the brain compared the firing rates of visual neurons that preferred leftward motion against those that preferred rightward motion.
Right.
In a subjective value decision, your prefrontal cortex compares the firing activity of orbitofrontal neurons encoding the value of the coffee against the activity of neurons encoding the value of the tea.
It is another firing rate competition? The coffee neurons are shouting against the tea neurons?
To observe this competition in real time, researchers design experiments that force subjects to make difficult trade-offs. Let's look at another monkey experiment. We start by finding a monkey that strongly prefers the taste of grape juice over apple juice. If you offer equal amounts, the monkey picks grape 100% of the time.
Okay, so grape juice is the high-value item. Apple juice is the low-value item.
The researchers then offer a choice, a very small volume of the highly valued grape juice versus a massive volume of the less valued apple juice. They are pitting quality against quantity.
Which forces the brain to do some serious math, like I love grape, but that is a lot of apple.
The researchers meticulously titrate the volumes. They adjust the drops of apple juice up and down until they find the monkey's point of subjective equality. This is the exact, specific volume ratio where the monkey chooses the small grape 50% of the time and the large apple 50% of the time.
So at that precise ratio, the firing rates of the grape value neurons and the apple value neurons are perfectly tied. The biological scale is perfectly balanced.
And when you observe the monkey's behavior at this specific point of subjective equality, two phenomena emerge that perfectly mirror the physics of perceptual decision-making. First, the decision takes significantly longer to make. The monkey hesitates, its eyes dart back and forth between the options. Second, the choices become highly inconsistent from trial to trial.
In the dot motion task, we called this the speed-accuracy trade-off. When the dots were moving randomly, the brain took longer to accumulate evidence, and it made more errors.
Here, because there is no objective correct answer, we call it the speed-consistency trade-off. When the subjective values are nearly identical, the brain struggles to accumulate enough evidence to cross a decision threshold, leading to long reaction times and variable choices.
Let me bring in a human analogy, because choosing between juices seems relatively simple. What about a massive, life-altering decision like buying a house?
Okay, good example.
Let's say I'm choosing between House A, which is a tiny fixer-upper in a great neighborhood with a short commute, and House B, which is a massive, beautiful home, but it's an hour away from the city. Why is my preference so fickle? Why do I wake up on Tuesday convinced House A is the smart move, and by Thursday night I am desperately drafting an offer for House B?
It happens to all of us.
If it's just a firing rate competition in my orbitofrontal cortex, why is the math so noisy?
Because the concept of noise in a value-based decision is exponentially more complex than the visual static of dots on a screen. Visual noise is just random fluctuations in photons. Value noise is driven by the fact that the value of an item is rarely monovalent. You don't value a house based on a single metric.
Right, you value the kitchen, the yard, the commute, the school district, the property taxes.
And all of those subvalues are shifting constantly based on your mood or what you read in the news that morning. Context modifies value instantly. If you are evaluating a glass of water, the value representation in your orbitofrontal cortex is relatively low if you just drank a soda. But if you have been running a marathon in the heat, the firing rate representing the value of that water will be blindingly high. Furthermore, value is heavily influenced by novelty and familiarity.
Like, I might love my neighborhood coffee shop, but if a new matcha place opens across the street, the novelty alone gives it a massive value boost.
Evolutionary biology calls this the value of exploration. To evaluate all of these wildly shifting complex parameters, the brain has to do something extraordinary. It has to engage in prospection and memory retrieval. When you consider House B with a long commute, your brain is non-consciously querying your memory banks for every time you've been stuck in traffic.
Oh, wow.
It is simulating the future, imagining how tired you will be driving home in the snow 3 years from now.
My brain is rendering an entire virtual reality simulation just to assign a value to the house.
And that simulation introduces massive, unavoidable variability into the evidence. Your memory of traffic might be particularly vivid today because you got cut off on the way to work. By Thursday, you might have forgotten that frustration, and instead you are simulating the joy of hosting a dinner party in House B's large dining room.
Right.
The evidence samples are wildly variable moment to moment, meaning the accumulator's constantly tipping back and forth before it ever has a chance to reach a definitive threshold.
So when I am paralyzed by indecision, it's not because my brain is broken. It's because the orbitofrontal cortex is processing such a chaotic, noisy stream of simulated futures that neither option can sustainably cross the decision bound.
That is the biological reality of indecision. The firing rate competition is locked in a stalemate.
This is a massive paradigm shift in how I view my own choices, but I want to pivot here because notice a pattern in everything we have discussed so far. We have been talking exclusively about actions. Deciding to carry an umbrella, deciding to move my eyes to a green target, deciding to reach for the grape juice or sign a mortgage. Every single one of these involves a motor output. But what about just knowing something is there, even if I never interact with it?
Oh. Okay.
Right now, I know there is a microphone in front of me. I'm not deciding to grab it. I'm not valuing it. I just know it exists.
Mm-hmm.
Does this framework of evidence accumulation explain the passive state of knowing?
This is where the underlying neuroscience takes a profound philosophical turn. We are moving into decision-making as a framework for states of knowing. And to answer your question directly, there is no such thing as passive knowing.
Wait, really?
The framework posits something that sounds counterintuitive. A state of knowledge is, in fact, a perceptual decision. It is a provisional commitment to a proposition based on sensory evidence.
A provisional commitment, but I don't feel like I am constantly deciding that the walls of this room exist. I just perceive them.
You understand why perception is an active decision. We must introduce the theory of affordances, pioneered by the ecological psychologist James J. Gibson. Gibson radically shifted how we think about vision. He argued that animals do not simply perceive the neutral, geometric qualities of objects in their environment. We don't just see a sphere or a cube.
So what do we see?
An object is perceived fundamentally in terms of the behaviors it affords the observer.
Affordances. Give me a concrete example.
Consider a simple stone resting on the ground. When you look at it, your visual cortex certainly processes its gray color, its texture, its roundness. But Gibson argued that your perception is defined by what the stone affords you. If it fits perfectly in your palm, it affords grasping.
It's a hand-sized rock.
If you are threatened, and the stone has a certain heft, it affords throwing as a projectile. If you are sitting on a park bench trying to read a newspaper on a windy day, the stone affords pinning the paper down as a weight. The affordance is the potential behavior of the animal in relation to the physical properties of the object.
So my perception of the stone isn't just a photograph. It is inextricably tied to what my specific physical body can do with it. A mouse, looking at that same stone, sees a completely different set of affordances. It affords hiding behind, not throwing.
Exactly, and modern neurobiology has found the physical hardware that proves Gibson right. We look to regions like the anterior intraparietal area, the AIP, located in the parietal cortex. Researchers have found that neurons here do not merely fire to register a generic shape or contour. They represent a provisional intention to act.
What does a provisional intention look like in a cell?
When you look at the handle of a coffee mug, your visual cortex sends the geometric data to the AIP. The neurons in the AIP essentially open up a submenu of your behavioral repertory. Specific neurons begin to fire that correspond to the precise hand posture, the exact curvature of the fingers, and the wrist angle required to grip that specific handle.
Wait, even if I have absolutely no intention of drinking the coffee, even if I am just glancing at the mug while walking past the table?
Yes, the visual information is actively interrogated by the parietal cortex to answer a continuous, non-conscious question: how might I interact with this? The firing of those specific AIME neurons is a provisional commitment to an affordance. You do not have to execute the motor plan. You don't have to reach out. But the knowledge of the mug, your understanding of what that object is constituted by that provisional motor simulation.
It's like my brain is a video game engine, constantly rendering interactive hitboxes around every object in my field of view. It's running a background simulation. This affords sitting, this affords opening, this affords grasping. And the act of recognizing the object is fundamentally the same thing as loading the motor plan to use it.
That is a brilliant analogy. The rendering of the hitbox is the perception. And this active rendering gives rise to a concept articulated by the French phenomenological philosopher Maurice Merleau-Ponty. He described what he called the temporal thickness of the present.
The temporal thickness of the present, it sounds incredibly poetic. How does it map to neurobiology?
It captures a stark physical reality about how your brain handles time. Raw sensory data from your retina is incredibly fleeting. Your eyes are constantly darting around in tiny movements called saccades. The actual pattern of photons hitting your retina changes completely every few hundred milliseconds.
Right.
Raw sensation has no temporal persistence. It is razor thin.
If my consciousness was just tied to my retina, my reality would be a chaotic, flashing strobe light of colors and shapes.
But you don't experience a strobe light. You experience a continuous, stable reality. Why? Because knowledge from higher brain regions, these provisional affordances rendered by the parietal cortex, has persistence.
Oh, I see.
Once your AIP neurons lock onto the affordance of the mug's handle, that state of knowledge persists even when your eyes dart away to look at your computer screen. The provisional decision about the object holds its state, giving your present reality a thickness, a continuity over time that is freed from the immediate bombardment of sensory input.
I need to unpack this with something even more fundamental than a coffee mug. Let's talk about color. How does the theory of affordances and provisional decisions apply to knowing that something is, say, the color red? That seems like a pure, passive sensory input. Red is just red.
It feels passive, but color is one of the most active computations the brain performs. We can see this through the phenomenon of color constancy. Think about looking at a ripe red apple resting on a picnic table.
Okay, I see it.
If you bring a physicist with a spectrometer to measure the actual wavelengths of light bouncing off that apple and hitting your retina, the objective redness changes drastically depending on the time of day. The spectral content of direct noon sunlight is completely different from the spectral content of a cloudy afternoon, which is wildly different from the golden hour of sunset.
Right. If I take a photo with my phone at noon and another at sunset, the actual RGB pixel values of the apple in the photograph will be entirely different. The evening photo will be bathed in orange and yellow light.
Your raw sensory neurons in the retina are easily fooled by this. They just obediently report the shifting wavelengths of light. But you are not fooled. You don't look at the apple at sunset and think, oh, the apple has physically changed its pigment to orange.
No, of course not.
You experience color constancy. You perceive the apple as the exact same shade of red all day long.
How is my brain overriding the actual physics of the light hitting my eye?
Because higher knowledge states in your cortex are not simply looking to measure a wavelength of light. The brain is looking for an affordance. What is the affordance of the color red in a natural environment?
For a primate foraging in a forest, well, red means fruit. It means calories.
Exactly. Red affords ripe vegetation ready to be eaten. The brain actively filters out the changing ambient light of the sun to solve a specific survival problem: is this food?
That makes so much sense.
The knowledge state of red is invariant to the changing light because it is inextricably tied to an action-based interrogation of the world. You perceive the redness constantly because your brain has accumulated evidence and made a perceptual decision, a commitment to the affordance of ripe fruit.
So perception is never, ever a passive camera taking a photo. It is a relentless, active interrogation. The brain is aggressively asking the environment, what does this mean for my survival and my body? And the answer to that question, The loaded motor plan, the filtered color, is the perception.
Yes. And the profound implication here, the unified theory of this entire framework, is that knowing, perceiving, and believing all share the exact same biological structure as a physical motor decision. They're all provisional commitments to a behavioral affordance, achieved by accumulating noisy evidence to a threshold.
Wow.
You decide to know the apple is there using the exact same mathematical accumulator circuits you use to decide to reach out and grab it.
Here is where it gets incredibly deep. If knowing is just a non-conscious decision about an affordance, if my parietal cortex is just simulating hand postures and filtering ambient light to find ripe fruit without me actively thinking about it, then what is consciousness?
Right. The big question.
Because most of the time, I walk through a room, I dodge the coffee table, I reach for the door handle, all without ever consciously thinking about those objects. I am navigating 10,000 affordances perfectly on autopilot. So what makes an affordance cross over from a non-conscious calculation into something I'm subjectively aware of?
That is the ultimate question of the chapter, understanding consciousness through the lens of decision-making. First, we must accept that you are entirely correct. You are navigating the world beautifully using pre-conscious, non-conscious decisions. Sigmund Freud famously quipped that consciousness is vastly overrated precisely because the majority of our most brilliant, complex computations happen not consciously.
Like when you are stuck on a crossword puzzle, you put it down, go take a shower, and suddenly the answer just pops into your head. The heavy lifting was done in the dark by non-conscious circuits. The conscious aha is just the final output.
Exactly. So we have to separate standard brain activity from actual consciousness. And neurobiology divides consciousness into two distinct phenomena. The first is what we might call neurology consciousness. This is baseline wakefulness, arousal, the transition from a coma or deep sleep into a waking state.
The lights are on.
Right. And even this is driven by a decision threshold. Consider a pair of exhausted parents sleeping through a heavy thunderstorm. Traffic is rumbling outside, thunder is booming, rain is lashing the windows. The non-conscious brain is actively processing all that auditory data, evaluating it, and deciding this is ambient noise. It affords no necessary action.
Okay.
But the moment their infant lets out a tiny high-pitched whimper from down the hall, both parents instantly snap awake.
Because the non-conscious brain filtered the audio, accumulated the evidence of the cry, and made a decision a baby crying affords a critical call to nurture, it crosses the threshold to trigger arousal.
Precisely. That is neurology consciousness. The brain decided to transition the entire organism to a state of wakeful engagement. But that is not what philosophers, poets, and neuroscientists mean when they debate the hard problem of consciousness. They are talking about the loftier phenomenon, subjective awareness. The sense of a unified me beholding the world, the rich internal movie theater of imagery and agency.
How do we get from a baby crying to the internal monologue I use to narrate my own life?
The hypothesis presented through this decision-making framework is startlingly elegant, though perhaps unintuitive at first. The theory posits that conscious awareness arises when the non-conscious brain reaches a decision to report an item.
To report it? You mean to speak? To say it out loud?
Not necessarily overt speech, to report it to another mind or to report it to yourself in the future. The core idea is that reporting is simply another provisional affordance, just like reaching, grasping, or looking.
Let me make sure I am visualizing this correctly. My brain registers the affordance of a coffee mug it affords gripping. I do that non-consciously while I am reading an email. My hand just finds the mug. But if I decide to turn to you and say, hey, look at this mug, that is a distinctly different affordance.
Yes. If the sensory evidence for the mug hits the threshold for the grasping affordance, you grab it like a zombie, without subjective awareness. You do this all the time while driving on autopilot. You brake for red lights, you turn the wheel, all non-consciously, because those objects hit the threshold for the avoidance or navigation affordance.
Right.
But they never hit the threshold for the reporting affordance, so you arrive home with no conscious memory of the drive. It is only when the sensory evidence crosses the bound to trigger the reporting affordance that the object pierces consciousness.
I need a highly specific scenario to really grasp this transformation. How does preparing to report something change it from a zombie action into a conscious experience?
The authors provide a brilliant, vivid scenario to illustrate this. Imagine a woman sitting entirely alone at a workbench. Resting on the table in front of her is a power drill.
Okay, I see the workbench, the woman, the drill.
Non-consciously, her brain is incredibly busy. The visual cortex is processing the geometry of the drill. The parietal cortex is registering its location relative to her hand. The AIP neurons are registering the affordance of the handle she could grasp it. Her amygdala might even register the sharp metal bit at the end. It affords danger,
Oh,
avoidance.
cool.
All of this is rich, highly complex knowledge. But as long as she's alone, it can all remain entirely non-conscious. If she reaches across the table for a pencil, her hand will naturally arc to avoid the sharp bit of the drill, guided purely by non-conscious spatial mapping.
Because her brain has provisionally mapped the affordances of the drill for physical navigation and survival. It is a completely private, first-person experience of utility.
Exactly. It exists only in relation to her body. But now, imagine a man walks into the room and sits down across the table from her.
The variable changes. Another person is introduced.
The woman's brain now provisions a new commitment. It entertains the possibility of reporting about the drill to the man. Can you hand me that drill? Or watch out for the sharp bit. This simple provisional intention changes everything because human beings possess a cognitive capacity known as theory of mind.
Theory of mind. The psychological understanding that other people are independent agents with their own thoughts, beliefs, and visual perspectives that are different from my own.
Crucially, different visual perspectives.
Uh-huh.
Because she possesses theory of mind, the woman knows that the man sitting across from her can see the back of the drill, a side that is completely occluded from her own vision. She knows he has his own spatial relationship to it, his own affordances for it. By provisioning a report to him, she must mentally construct the drill not just from her perspective, but from his.
Oh, wow. The drill ceases to be just a private collection of sensory data and motor plans tethered to her own hand. It becomes a shared object.
Yes. The drill undergoes a profound cognitive transformation. It shifts from a subjective sensory experience into a thing in the world. It now possesses an existence independent of her own mind. It is a public object occupying shared space. The hypothesis is that this state of knowledge, this specific framing of an object as existing in a shared reality because we are preparing to incorporate it into a report, is the exact physical mechanism of what we experience as conscious awareness.
But wait, I have to challenge this. Reporting implies language. It implies telling the man about the drill. Are you saying we only have conscious experience because humans evolve complex vocal cords and syntax? What about animals? A dog certainly seems conscious. Or what about me just sitting alone on a mountaintop, watching a sunset, feeling the warmth of the sun on my face without any desire to tell anyone about it? Am I not conscious in that moment because I'm not speaking?
It is the most common and vital pushback to this theory, and the distinction lies in the word provisional. The intention to report is a provisional capacity. No overt speech, no pointing, no physical gesture actually needs to occur. Just as your AIP neurons can map the complex affordance of grasping a mug without you ever moving your arm, your prefrontal cortex can map the affordance of reporting without you ever opening your mouth.
So it is the hardware capacity to frame the object as reportable, not the act of reporting itself.
Exactly. And the foundation of reporting is the capacity to frame an object within a narrative. Narrative is the engine of consciousness. When you sit alone on that mountain and consciously feel the warmth of the sun, you are making a mental note to yourself. You are reporting to your future self. You are incorporating that feeling into a narrative timeline. You are assigning it history, prediction, origin stories, and consequences.
So my internal monologue says, the sun feels warm today because it is finally spring, or I will remember how beautiful the sunset is when I'm back in the cold office tomorrow. I am narrativizing the sensory input.
Right. Narrative allows us to reason in profoundly complex ways. It allows us to hold an object, an event, or a feeling in our mind as an independent entity with a past and a future, detached from our immediate physical survival. The raw brain activity itself, the sodium and potassium ions flowing across membranes, the firing of neurons is not conscious.
Makes sense.
But the mechanism of consciousness is just a decision threshold. When the accumulation of evidence crosses the threshold for the affordance of sharing with another mind or incorporating into a narrative timeline, that specific elevated state of knowing is what we call awareness.
This dismantles so much mystical thinking about the brain. Consciousness isn't some magical glowing aura located in the center of the pineal gland. There is no consciousness neuron.
The authors are explicit about this. There is no scientific reason to search for a magical anatomical area that bestows consciousness, or a special quantum oscillation frequency, or a mystical ingredient. The architecture of consciousness likely looks exactly like any other provisional motor commitment. It is just a decision threshold reached by bounded accumulation. But instead of the decision output being flex the bicep or move the eye, the decision output is narrativized.
That is incredibly elegant, but honestly, it's also a little humbling. The deepest, most profound mystery of the human condition, the poetry we write, the angst we feel. Our entire sense of self might just be a repurposed neural circuit originally designed to help a primitive organism decide which way a flock of birds is moving.
Evolution is the ultimate pragmatist. Biology is remarkably efficient at taking simple, robust mechanisms like accumulating evidence to abound and duplicating them, expanding them, and repurposing them for infinitely more complex functions.
This has been a staggering journey. We have scaled up from the physics of light to the philosophy of the mind. So instead of just running down a bulleted list of topics, let's weave this all together. Let's trace the full life cycle of a thought based on everything we've learned in this deep dive.
It starts at the very periphery of your body. Raw, noisy, sensory evidence photons bouncing off a coffee mug, or sound waves from a weather forecast hit your receptors. Your sensory cortex processes these fragments, but they're fleeting, possessing no temporal thickness.
And then the accumulation begins.
Yes. That noisy evidence is fed deeper into the brain, to the parietal and prefrontal cortices. Here, neurons act as biological abacuses. They physically hold and update their firing rates, integrating the data over time. If you're making a complex probabilistic judgment, these synapses act as logarithms, adding up the weights of the evidence.
But if I'm making a subjective choice, my brain looks inward. The orbitofrontal cortex weighs the item's value based on past memories and future simulations, while my striatum calculates the physical effort to get it. This introduces massive, noisy variability as the scales tip back and forth.
Regardless of whether it's an objective or subjective choice, the brain is constantly interrogating these inputs to generate affordances. The anterior intraparietal area provisions motor plans, simulating grasping, avoiding, sitting. These provisional commitments give the object persistence. You know the object is there because you have non-consciously modeled how to interact with it.
And for 99% of my day, that is where the process ends. I navigate the world as a highly efficient, non-conscious survival machine. But occasionally, the accumulated evidence for an object or a thought crosses one final specific threshold.
The affordance of reporting. The brain prepares to share the object with another mind, utilizing theory of mind to grant the object an independent existence. It weaves the sensory data into a narrative of past and future. And in that precise moment of crossing the threshold to narrativize, the lights come on. You become subjectively, consciously aware of the thought. That is the architecture of cognition.
It fundamentally changes how I view my own reality. I am building my awareness, one noisy, microscopic sample of evidence at a time. The next time I reach for my keys on the counter without looking, I'll know my parietal cortex just solved a massive calculus problem, rendering a spatial hitbox and a provisional hand posture in a fraction of a second.
And if you stop to actually look at the keys, to notice the way the light hits the metal, to remember who gave you the keychain, you've triggered the reporting affordance. You have brought a dead piece of metal into the rich narrative of your conscious reality.
Which brings us to a final, somewhat haunting thought to mull over as we conclude this journey. The capacity for narrative, simulation, and theory of mind, the very biological foundations of our consciousness, gave humans a massive evolutionary advantage. It allowed us to reason probabilistically, to build agricultural systems, to invent science, to coordinate societies. But the researchers point out a very sharp caveat about this cognitive superiority. They say it is an evolutionary advantage, at least for the time being, until it leads us to make the Earth uninhabitable.
It is a dark, poignant observation on the double-edged sword of high-level cognition. Our ability to simulate the future allows us to extract resources at an industrial scale, but it also forces us to foresee the catastrophic consequences of those actions.
It's the ultimate paradox. If our consciousness is built fundamentally on our neural ability to simulate future realities and narrativize them, are we biologically doomed to simulate our own end? We can see the climate data. We can accumulate the evidence. But the noise in our value systems, economic profit versus long-term survival, keeps us paralyzed in a speed consistency trade-off. We can't cross the decision threshold to act. Or is that very same neural architecture, our unique ability to project a shared reality, report it to others, and change our provisional commitments, the only tool we have capable of preventing it?
The defining feature of this entire decision-making framework is that a provisional commitment can be updated. We have the biological capacity to change our decisions before taking action based on new evidence. The freedom from the immediacy of the present moment, the ability to rewrite the narrative before it happens, is the true definition of cognition.
We just have to hope we accumulate the right evidence in time. I think back to where we started today, that comforting binary medical x-ray. We look at a broken bone and we know exactly what it is, black and white. The human mind isn't like that. It is muddy, it is relentlessly noisy, and it is constantly calculating invisible probabilities just to figure out what a coffee mug is. But in that noise, in that continuous microscopic voting process of billions of synapses firing in the dark, we find the flexibility to change our minds, to share our narratives, and to consciously experience the beauty of the world. Thank you for joining us for this advanced two-part exploration into the physical machinery of cognition. We will leave you to ponder the weight of your own thoughts until the next deep dive.